see a table of counts for different individuals in the class, counting the time down a ramp when a domino is laid flat on its side, when it's laid along its long edge, and when it's laid along its short edge. Flat, long edge, short edge. And we see the counts. Don't have to read those to you. So we get the approximate slope of the graph, of the v versus t graph, and let's approximate slope v versus t, a little hard to read, but we get these approximate slopes on our v versus t graph, assuming a length of 60 centimeters, and of course we do the usual thing that we've already done. We know our average velocity goes here, and our final time, if we start at 0, goes here. From this, we conclude that the slope is double the average velocity divided by the final time. We also look at the trapezoid where we have an initial velocity that isn't 0. This depends on the initial velocity being 0. This is the more general result, and it's based on the idea that the spacing of V0 and Vf has Vav in the middle, so that the difference between V0 and Vav, which is Vav minus V0, or the change from V0 to Vav, is the same as the change from Vf to Vf. So that's Vav minus V0. So that Vf is Vav minus V0 plus Vav, and here we have it. So that we get this. Now, why are we using Vav? It's because from our time and the length of our ramp, we immediately get average velocity, and from that we can conclude the final velocity, which in this case would be double Vav, and in this case, this is the final velocity, 2 Vav minus V0. Now, from that, we can get our V of t, which is slope times t plus the v-intercept. In this case, that would just be at. And then, especially for university physics students and anybody else that knows calculus, if we integrate v of tau d tau from 0 to t, it's very straightforward. We get 1/2 at squared plus c, because we're integrating this. Okay, and if we integrate this, it's very clear that that's what we get. We're integrating at. And actually, I didn't complete the integral. This is evaluated from 0 to t, and it should be 1/2 a tau squared, because it's integrating v of tau. So I wrote this down quickly without thinking. And when we do this, we get 1/2 a t squared. So that is our v of t. It turns out not our v of t. When we integrate the velocity, it turns out that we get the position. So the position would be this, and we don't have to do a lot more reasoning to get the position function. Okay. Now, we calculated slopes of v versus t graph here and here, and from that we calculated the acceleration on each ramp. Acceleration is the slope of your v versus t graph, which is, in this case, this. So we do the 3 accelerations here versus the 3 ramp slopes, which I calculated for you, but it's very easy to calculate. It's the slope of the ramp, the rise of the ramp divided by the run of the ramp. When we did this, everybody, or just about everybody, I think everybody got an equation that either was very obviously well fit by a straight line or very nearly so. And this is, in fact, what we would expect for reasons that we don't know right now, we haven't developed right now. So one check of consistency of your data is whether you have a good fit by a straight line, good fit to this graph by a straight line. Another is that you have nearly equal slopes. So one test of consistency is that you have a good fit. Second test of consistency, you have nearly equal slopes. and I ask people to calculate the slope here, the slope here, these representing the 3 points. You will not generally have equal slopes due to the fact that you have a lot of uncertainty in this data. You're only counting whole counts, and some things are as short as 3 counts, and this means that your time interval, even if your count is completely consistent, has a possible error up to about 16%, even if you do it very accurately. So, anyhow, for that reason, you're not going to get equal slopes, even if they ideally would be equal, even if for your actual setup, the slopes of the graphs, if calculated with complete accuracy, with completely accurate data to an infinite number of significant figures, here, here, and here, we would expect your slopes to be almost equal. To at least a few significant figures, they would be equal. They wouldn't be quite equal because acceleration does change a little bit with friction, and friction changes a little bit with velocity. I mean, yeah, okay, so, but you have a slope here, and then a slope from here to here. People calculated these and got reasonably consistent results. For example, the data we have here gives us approximately 200 for the first slope, 150 for the second slope, 170 for the slope from here to here. Now that would be in units of centimeters per count squared, that is a unit of acceleration, whatever your count might happen to be. So a big question, is acceleration a linear function of slope? We have a pretty good indication that that's the case for at least this range of slopes. There's another reason this wouldn't be exactly the same, because it really isn't quite linear, but for small slopes below 1/10, it's pretty close to linear. It's actually a sine function. So is acceleration a linear function of slope? We want to test that more accurately, and of course we did that in lab using the computer interfaces, or the Vernier interfaces, to measure the time between the sound of starting and the sound of stopping.